All right, so here we have a problem where we're using conservation of mechanical energy, but the thing that's new here is we're talking about rotational kinetic energy, and we're including that in our problem. So here's a typical Atwood machine. It's just simply two blocks connected by a rope hanging over a pulley. Mass 1 is smaller than mass 2. But the trick here is now we're sort of acknowledging the fact that the pulley has an inertia to its rotation. And so we're asked to treat that as well. So we're going to think about the fact that as these two blocks start moving, some of the kinetic energy of the system is going to go into the rotation of the pulley, which we're going to treat as a solid cylinder. And that has a moment of inertia of 1/2 mr squared. So we're told that in this problem, the initial height of the two objects, the height 1 for mass 1 is 1.5 meters off the ground, where height 2, that's the height of mass 2, is 0.9 meters. And what we're going to do is we're going to allow block 2 is going to fall 1/2 meter. So we're going to, what are we going to do? We're going to do conservation of energy because there's no mention of any sort of friction in this problem. And so we're going to be thinking about, what kind of energy does everything have at first? Initially, it says the blocks are released from rest, so the kinetic energy is 0. But both of these blocks absolutely have potential energy. I'm just going to write it in symbols because we're going to see that we can actually simplify this a lot moving forward, so there's nothing to be gained by doing a bunch of calculations. Even if you don't believe me, I'm going to tell you that's true. Now, the kinetic energy is an important term to think about once the blocks are moving. So what we're going to do is everything's going to move this way. And block 2 is going to fall 0.5 meters. Block 1 is going to rise 0.5 meters. So, but at the same time, they're going to be moving, and the pulley is going to be rotating. So I'm going to first of all talk about the motion of the two blocks. They have to move with the same speed because of the fact that they're attached together. And I have found in some problems when you are faced with a system like this, it's connected by a rope, but you're asked for the speed of one of the objects, you tend to ignore the kinetic energy of the other object, which we can't do. In fact, the speed that this system will achieve is basically going to be dependent on the fact that both of the blocks have to be moving. And so you can't just ignore one of them. They're connected. They're intertwined, both literally and figuratively. We also are going to have the rotational kinetic energy of the pulley. So we have to deal with that. And then I also have the potential energy of the two blocks. Now, block 1, M1G, it's actually going to rise 1/2 meter. So I'm just going to say H1 plus 0.5. And we'll see how this is going to help me later on. And block 2 is falling 1/2 meter, so it's M2G, and it's H2 minus 1/2 meter. Now, the reason that I did that is because then I have an MGH1 and an M2GH2 on both sides, and so I can actually kind of get rid of them. And so I'm going to have, for right now, I'm going to have 0 equals 1/2 M1 plus M2 V squared plus 1/2 I omega squared. I'm going to have plus M1G times 0.5, and then I go to minus M2G 0.5. So what I've done is I've eliminated the H1 terms on both sides. If that doesn't make sense to you, distribute out these terms here, and then simplify, and you should get to this stage as well. But I'm going to take these two things over to the other side because I want to solve for velocity. It's going to have m2g times 0.5 minus m1g times 0.5. I have 1/2 m1 plus m2 v squared plus 1/2 I omega squared. Now you might be a little worried that we have an omega here, but we're going to get rid of that in a minute. I am going to try to simplify this left-hand side. I can write it as m2 minus m1 times g times 0.5. So I've just kind of simplified that a little. I have 1/2 m1 plus m2 v squared. Now I'm going to substitute in for I is 1/2 mr squared, because that's the moment of inertia of the pulley. And omega can be written as v over r, and that's all squared because omega was squared. And this is going to simplify things a lot. So I'm going to come over here just to have a little more room. I have m2 minus m1 times g times 0.5 equals 1/2 m1 plus m2 v squared, and then 1/2 times 1/2 mr squared times v over r, but that's squared. So these r's are going to cancel out. Turns out nobody even cares about how big the pulley is. And so this ends up to be 1/2 m1 plus m2 v squared, and then this other term is 1/4 big M, that's the mass of the pulley, v squared. So we're almost to the point where we can sort of simplify this and solve for v. I'm just going to solve for v squared first, and I'm going to get m2 minus m1 g times 0.5, and then I'll divide it by 1/2 m1 plus m2 plus 1/4 big M. So if I simplify this, m2 minus m1 is 5 minus 1 times 9.8 times 0.5, and then 1/2 m1 plus m2 is just 3, and then 1/4 of the mass of a pulley is just 1/2. And so I get v squared is 5.6, and so I can take the square root to find the speed of the whole system, which is going to be 2.37 meters per second. So important things I wanted you to notice is that when this system starts moving, we have to account for the kinetic energy of both of the masses. And also the idea that when we substitute in for the moment of inertia and for omega, often things will really simplify. And while at first it seems like omega is another unknown, because it's related to the linear velocity, we can eliminate it pretty easily. And that allowed us to finally solve for our final speed of 2.37 meters per second.